two resonance structures for the formate ion, which is formula here. Carbon is the central atom, and describe how these structures relate to the true nature of the carbon-oxygen bond. Instead, we're going to do nitric acid, but the same type of question. And for nitric acid, nitrogen is the central atom. And the hydrogen is bonded to an oxygen. And I have to tell you this because otherwise it's not clear how you should set this molecule up. And your default position is that if you have are asked to do a Lewis structure, then you always have all of the atoms surrounding one central atom. And so that's why these hints have to be given if you were to be given a problem like this. And what that means is, so nitrogen compared to oxygen is the least electronegative. Put the three oxygens around it. And I'm giving you this clue because you do not put the H here. You attach the H to a hydrogen, to an oxygen. And we will see this enough that we will get pretty comfortable with it, though if this were on your exam, I would still have to tell you this, or I would tell you this. It turns out that many, so this we know, what do we know about this? This is a strong acid. That means that this H plus is going to come off 100%. And typically those acidic H's or H pluses are bonded to oxygens. And I'll write typically here because we will see exceptions. But it turns out it's much more likely to be bonded to an oxygen than to a nitrogen when both of those are options. Okay. Well, once you know your basic shape, oh, I forgot to add up my valence electrons. Let me do that. Hydrogen has 1. Nitrogen is in group 15. It has 5. Each oxygen has 6, and there are 3 oxygens. I end up with 24. Yep. And I have 2, 4, 6, 8. I'm going to now sprinkle the rest of my valence electrons around. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So tempting to put 2 more electrons on this central end so that it has an octet, but I am only allowed 24. Do not pass go. Do not collect $200. Yeah, we're done with putting electrons in. Now, okay, next step is to complete octets. We're not ready to do a formula charge analysis yet. But we'll put in, because nitrogen does not even have an octet yet. So complete octets. And what this looks like is, so we're not going to mess with this part over here. We're going to take one of the pairs from one of these oxygens over here. Let's just take that one. So now there's a double bond between these two. And single bonds between the other 2 oxygens. And then hydrogen. Hydrogen its version of the octet rule is that it wants to have 2 electrons, which are the same number of electrons as helium. So hydrogen wants 2 valence electrons, same as helium. We're not done yet. We haven't done a formal charge analysis and labeled our formal charges, our non-zero formal charges, that is. If you look down here, you see an oxygen, and this will be our third one of these, by the way, which is an oxygen with 1 bond and 6 valence electrons. Formal charge on this oxygen is going to be 6 minus 1 bond and 6 unshared electrons. We get a -1 formal charge for this oxygen. We've seen that before. We're not surprised. We put it right there. The other 2 oxygens, by the way, have 2 bonds and 4 unshared electrons. This oxygen has a formal charge of 0. This oxygen has the same formal charge, 0. If you do a formal charge analysis on hydrogen, you would see that it has a formal charge of 0. Now we do a formal charge on the nitrogen. It's in group 15, so it has 5 valence electrons from the periodic table. It has 4 bonds plus 0 unshared electrons. Its formal charge is +1. And so we put a little plus here. Now, we want to minimize formal charge. We look at our periodic table. We look at where nitrogen is. We see that nitrogen is in the 2p area of the periodic table, and 2p atoms cannot have expanded octets. And so, let's see, nitrogen cannot have an expanded octet. And this is the best Lewis structure for nitric acid. Now, like I said, everything is based on getting the best Lewis structure. We haven't even answered the question yet. Now let's address the actual question. It says draw the 2 resonance structures. Well, there are 2 resonance structures here. Let me describe what resonance structures are. So resonance structures are same bonding pattern, different arrangement of electrons. Same bonding pattern, different arrangement of electrons. And now let's talk about how that applies to our best Lewis structure down here. For our best Lewis structure, if you remember when we made this double bond, we had a choice. We put it here, but we could have put it down to this oxygen. And in this course, so resonance structures basically says if you have a choice where to put a double bond, draw all choices. So if you have a choice where to put a double bond, draw all choices. And I'll put a little colon there because that's what we're going to do. I'm going to start by redrawing this Lewis structure exactly as it is. I hope. And then I'm going to draw what I and many people call resonance structure arrow. And now I'm going to draw the double bonds down here and a single bond over here. Like I said, it's the other choice. Oh, and I got to draw my formal charge, by the way. So I still have to draw my formal charges in here. So these two are the resonance structures for HNO3. Resonance. These are the two resonance structures. And so I guess we're not quite done, but any questions about these resonance structures?
On the original problem with the, what is it, HCO2 ion,
Yes.
would the resonance structure just basically be switching where the hydrogen bond would be on the oxygen?
It will be a little different than that, Selden. So I would guess that when you get, so this H is actually bonded to the carbon.
Okay.
Does that help? Or
That will help.
Do you want to explore that option and we can talk more?
I will do that.
Okay.
All right, thanks.
Yeah. Okay. So then we come down here. And the question says, and describe how these structures relate to the true nature of the carbon-oxygen bond. We are going to talk about the true nature of the nitrogen-oxygen bond, and specifically these two. So, and the way in which we're going to do that, and I'm going to have to create more space since these are the longest problems ever. All right. So the way in which you do that is you circle the same bond in each resonance structure. And determine its bond order. And my abbreviation for bond order is BO. So and I'll do this part, I guess, in black. So if I circle this bond in both Lewis structures, I can see that I've got a double bond on one side and a single bond on the other. So bond order is going to be equal to number of bonds divided by number of resonance structures. So I have 1, 2, 3 bonds. I have 2 resonance structures. My bond order is 1.5. If I do the same thing here, I get bond order, and I'll do this one in red. I get 1, to 3 bonds. I get 2 resonance structures. Bond order is also 1.5. And so the conclusion, or conclusions, we have 2 conclusions. One, so each of these 2 bonds has the same bond order. And let's see, 2. These 2 bonds are identical. Okay. And the reason this is important is because if you just drew one of these Lewis structures, let's say this one, you would think that we have a double bond in one position and a single bond in another. And the true nature of each of these bonds is that they each have a bond order equals 1.5, and these 2 bonds are identical, so there's no differences between these. If you were to look at any kind of method of evaluating, say, the length of these bonds or the energy of these bonds, you would find they are both exactly the same. And then I guess the last thing I'll add in here is as bond order increases, so the bond length decreases, and bond strength increases. And so the way in which you would tell that this is a 1.5 bond is because it would have a length halfway between a nitrogen-oxygen single bond and a nitrogen-oxygen double bond. So I think that's everything I wanted to say about this. Like, there's 2 main points. Can you draw the resonance structures? And do you know what it means? And what you can think of is you look at all of the resonance structures, and this is why, by the way, it's important that when you draw different Lewis structures, you draw all of the atoms, that's the O, N, O, H, and O, in the exact same positions, the exact same bonding pattern. Because the only thing that changes is the arrangement of the electrons. So you would never draw this with the O up as a different resonance structure. That is not, that's just different. And it makes it confusing to tell when the resonance structure is present or not. Okay, I think that's all I had to say about this problem. Anybody got any questions? Or Daryl, I don't know if that worked out for you. Sorry, Selden, I don't know if that worked out for you, finding the correct resonance structures.
Yeah, I think I got it now. Thanks.
Sure, good.